Hello, abstract algebra students. In this video, we will begin the proof that M2R is closed under matrix multiplication. Okay. This will be the last proof in showing that M2R is a non-abelian semigroup under matrix multiplication. So let's go to a new page on our virtual blackboard here and begin. Our claim is that the set M2R, the set of 2 by 2 real matrices M2R, is closed under matrix multiplication. So if we apply the definition of closure to the set M2R under matrix multiplication, what we want to show is for all AB, if both A and M2R and B and M2R, then A times B is also a member of M2R. Okay. So A and B are capital because they're matrices. So let's let AB be given. Without loss of generality, make that A and B are the following matrices. Okay, so A is going to be the matrix ABCD. And B is going to be the matrix EFGH. Our convention that we always use, counting the entries in matrices as lowercase letters, starting at the beginning of the alphabet. Now that we've let A and B be given and unraveled it, we'll assume the if part. So assume both A and M2R and B a member of M2R. Since we know that both A is a member of M2R and B is a member of M2R, by the definition of M2R, it follows that now we know a lot of entries. We know a lot about the entries A, B, C, D, E, F, G, H here. Because the matrix A, B, C, D is in M2R, it means each of the entries A, B, C, and D are members of the reals or in R. And similarly, because the matrix EFGH is in M2R, it means each of the entries are in the real numbers. So we know that A is a member of the reals, B is a member of the reals, C is a member of the reals, D is a member of the reals, from the matrix A being an M2R. Then we know E is a member of the reals, F is a member of the reals, G is a member of the reals, and H is a member of the reals, from the matrix B being an M2R. Now, once we know all of this, our goal is to show that A times B, the matrix, is a member of M2R. And I don't see right off the top how I'm going to do this. So again, I'm going to get some virtual scrap paper here. And I'm going to work backwards from what I want to show. So I want to show that A times B is a member of M2R. Remember, M2R is the set of matrices. R is the set of numbers. So to show that A times B is a member of M2R, I need to show that the matrix A, B, C, D times the matrix E, F, G, H is a member of M2R. Now, let's actually do this matrix out. When I do this out, I get AE plus BG. I get CE plus DG. AF plus BH. CF plus DH. So I need to show that that matrix is a member of M2R. But then I think, wait a minute, what does it mean for a matrix to be in M2R? It means it has to be a 2 by 2 matrix, which this obviously is. But it also means that the 4 entries have to all be real numbers. So let's take a closer look there. For the 4 entries to be real numbers, AE plus BG needs to be in R. AF plus BH needs to be in R. CE plus DG needs to be in R. And CF plus DH needs to be in R. So, working backwards from where we want to end up, we figure out that it is sufficient to show that these 4 numbers are all in R. And that tells us what we need to do. We need to take the fact that these 8 things, A, B, C, D, E, F, G, H, are in R, and build up that these expressions are members of R. And we will do that in the next video. Stay tuned, more to follow.